recording. I will put it on YouTube once it's done. Okay, now so let's get it started. So the Laplace transforms. Now, the reason why we have to study Laplace transforms is that we could use Laplace transforms as a tool to solve linear time invariant system problems. Okay, sometimes solving LTI systems in the time domain is complicated, as we have seen when we did convolution. Okay, nobody wants to do convolution because it's so complicated. Sometimes it doesn't give you insight to the problem. So we're gonna use another method, which is to transform the signal and the system. Instead of working in the time domain, we will transform it into an S domain, okay, into another domain, and work on the S domain. And you'll find that working in the S domain is a lot easier than working in the time domain. In the time domain, to find the output, right, you have to do the convolution integral. But in the S domain, the process of doing integral will reduce into just algebraic manipulation, as we will see. All right, so the diagram is this: problems, okay, to be solved. We have a problem to be solved, right? Usually it's in a time domain, right? And then we use Laplace transform to convert it into an S domain. So this is time domain. This is time domain right here. Now, after the Laplace transform, right, it is in an S domain. Okay, and then once we get the Laplace transforms of all the things that we wanted, we're gonna have to solve just algebraic equation. Okay, if we don't do Laplace transforms, if we direct this output into this, then we cannot solve it by algebraic equations. We have to do convolution integral, right? And we know that we don't like that. We don't want to do convolution integral. So using Laplace transforms enables us to solve the problem using algebraic equations, which is a lot easier. And once we have done the algebraic equations, then what we have to do is we have to convert it back into the time domain, because everything here is in the S domain, right? So we have to convert it back to the time domain. The process of converting back to the time domain is called the inverse Laplace transform. Okay, and once we do that, we have the solution. All right, so from here to here, this is an S domain. Okay, and from here to there, this is time domain. This is also time domain. Now, the question is, how do we convert? How do we do this? Okay, we know that it should be easy. Okay, I trust you that it's easy. It's gonna be easier. I trust you, right? But the question is, how do I find the S domain? How do I transform a signal from time domain into the S domain? We're going to be using what's called a Laplace transform. So let's look at the definition of the Laplace transform. Suppose we have a signal, we have a function x, right? X is a time function. Okay, x is a time function. Then the Laplace transform is denoted by this integral. Now, what to do? What you do is that you have a time function x, which you want to convert from the time domain. You have x here. Okay, you have x here. You want to convert it into an S domain right here. So what you do is you do this process, right? This process is actually this integral. This integral is this box here, the Laplace transform. So what you do is you put the signal, the function x, inside this integral, and you multiply it with e to the negative st, and you integrate it over this interval. Now, the integration, a couple of things that you have to understand. First, the integral is with respect to time. Okay, the integral is with respect to time. So time here can be thought of like a dummy variable. Once you've done the integration, time should disappear. Okay, you shouldn't have any time out of the integral because we have a boundary, the ceiling and the floor already. So time, that should not be time once you've done the integration. Time should be gone. But the thing that will come out of the integration is the variable s here. Okay, because we're not integrating with respect to s, right? We're integrating with respect to time. So s will come out. So that means that this integral would be a function of s, right? The integral is going to be a function of s. And because it is a function of s, we will call it x of s. Okay, we'll call it x of s. Because it's a function of s, right? S will come out of the integral. So it is a function of x. That's why I write it down, x of s. Okay, and time is gone, so it's not a function of time. That's one thing. That's the first thing that you understand. The second thing is, what does it mean by zero negative here? Okay, zero negative here means just before time zero. Arbitrarily before time zero. Just before time zero. Including zero, right? Including zero, but not negative 0.1, not negative 0.01, not negative 0.001. Just a little bit before time zero. So that's what it means by zero negative. If I put down zero positive, if on the other hand, if I write down zero positive, it would mean just a little bit after time zero. So negative means before time zero, positive means after time zero. But here in this case, so this integral here will include time zero, just a little bit before time zero until infinity. That's the second thing. The third thing is that the third thing has to do with the variable s here. Okay, s is a complex variable. So what it means is that the value of s would be a complex number. Okay, the value of s is a complex number. So I can write s as in two parts, right? S is equal to sigma plus j omega, where sigma is the real part of S and omega is the imaginary part of S. Okay, so S here is a complex number, it's a complex variable. Right, so this is the Laplace transform of, this is the definition of the Laplace transform. You should remember it. Okay, this is important. This is very important. Now, and we also use this notation, right? We have xs equal to, we use this notation, right? To mean that it is a Laplace transform of xt. So whenever you see the capital L here, okay, it means that this is the Laplace transform of the signal xt, and it is this integral. Okay, so this is how we say it is a Laplace transform. This is called a Laplace transform operator. And sometimes we write this one down. Xt has a Laplace transform of xs. Sometimes we write this one down, means that these two guys is a Laplace transform pair. Okay, this is a time domain signal. This is the S domain signal. They are a pair. They belong to each other. So when I say that they belong to each other, that's D. All right. It means that if you know XS, you can specifically determine XT without ambiguity. It is a one-to-one function. It is a one-to-one mapping. Okay, these two belong to each other only. Right? They're not polygamous. They belong to each other. If you know this, then this is the only one that pairs with XT. On the other hand, if you know XS, then this guy is the only one that pairs with this. Okay, and this is important. Also, if you know XT, right? If you know XT, then you can find XS by doing this integration. On the other hand, if you know XS, then you can find XT, okay, by doing what we call inverse Laplace transform of XS. Now, mathematically, to find XT out of XS would be very difficult because you have to do complex integration, complex variable integration, and you have to find residue. And that would be very difficult. So we will not go into that path. We will not find xt by doing integral. But instead, all right, if you know xs, to find xt, we will be using tables. Because we know that they belong to each other, right? So what you have to do is just look at xs and look up the table. What is this? All right, then you're going to find xt here. So this is how we do the inverse Laplace transform. Okay, so we use tables to do inverse Laplace transform. So this is called the inverse Laplace transform of the function xs. Okay. Now let's do a couple of examples. The first example is about finding the Laplace transform of the unit impulse. The unit impulse signal. Okay. Now, what do you remember about the unit impulse signal? Okay, the unit impulse signal is a signal that has the notation delta, right? Do you remember delta, what it is? Yeah, all right, I hope so. So the Laplace transform of delta, all right, by definition, it is the integration from 0 negative, right? Just a little bit before time 0 until infinity. And then you have to look here. Okay, this is the thing that you want to transform, right? So whatever seen here has to be put into the integral right here. So you're seeing delta, right? So we know that we have to put delta here. Okay, and then the rest would just follow, which is e to the negative st and dt. Okay, and now we could use the property of delta, right? Because we know delta exists only at time equal to 0. Okay, delta exists only at time equal to 0. So we can plug in time equal to 0 here, right? So that is equal to integration from 0 negative to infinity delta t dt. Right? Going from here to here was because I just plugged in t equal to 0 to the exponent of this exponential function. Because we know that delta exists only at that time, right? And now, to find this integral, we just look at the interval over which the integration is done, which includes 0, right? This integration includes 0 because the way we define 0 negative. So we know that this is actually the area under delta, which we know it is equal to 1. So this is equal to 1. Okay, so we have the first Laplace transform pair, which is delta, right? Has the Laplace transform of 1. So this is the first one that we know. All right. In other words, if you want to find the inverse Laplace transform of 1, what are you going to get? If you want to find the inverse Laplace transform of 1, you're going to get delta. Okay? All right. Oh, well, second example. The unit step, right? The unit step. Do you remember the unit steps? It's a signal u. Okay, the unit step has a value of unity, which is 1, starting from time equal to 0 until infinity. Okay, now we want to find the Laplace transform of the unit step signal. Okay, so from definition, it is equal to integration from 0 negative to infinity. And then because we want to find u, right? So you put u in the integrand and e to the negative st dt. All right. And now, because of the definition of u, right? It is 1 when time going from 0, right? So we put 0 here to infinity, and over this interval u, the value of u would be 1. So we can just drop u from the integrand and put e to the negative st here, which is what's left. Okay? And then you have to do the integration, which we know that it is equal to negative 1 over s. Okay? And e to the negative st, right? And t going from 0 to infinity. And this is equal to minus 1 over s e to negative infinity times s minus e to the 0. And we know that e to the 0 is equal to 1. Now, we have to think about this guy. Okay, this is not as easy as it looks because this guy will converge to 0 when S is positive, right? If S is negative, this guy will not converge, right? So this is going to be 0 if the real part, remember S is a complex value. So when we say S is negative, we mean the real part of S is negative. It's positive, sorry. Positive. Okay? Actually, I think I do it the other way around. Sorry. I have to. Sorry about that. It has to be the other way around. Okay? So we have 1 over S. Now the condition is the real part of S is positive. So this is the Laplace transform view. So we can make a conclusion now that ut, which is the unit step signal, has the Laplace transform pair of 1 over S. Okay, and I think in this course we can drop the convergence criterion there. You don't have to care about the convergence criterion. And the inverse Laplace transform of 1 over S would be ut. Okay. Now, let's do this example before we move on. Example. Given x equal to one S plus 1 over S. Okay, we want to find x of t. Can you do this? If I give you xs as s plus 1 over s, right? Can you find xt? Can you do that? Now, the point is that the trick is that try to rearrange this, try to write this so that it would appear in a form that we already know. Now, what have we known here? Now, we know 1 over s, right? We know that the inverse Laplace transform 1 over s is ut. We also know that the inverse Laplace transform 1 is delta. So the question is, can you rearrange this function so that it appears as 1 over s and 1? Can you do that? Of course we can, right? So the solution is to write 1 plus s over s as 1 plus 1 over s, right? And then we take the inverse Laplace transform on both sides. Okay, so that means that xt, right, is the inverse Laplace transform of xs, right? And then instead of plugging in s plus 1 over s in the parentheses, we plug in this guy in the parentheses. Okay, so it is going to be inverse Laplace transform of 1 plus 1 over s. And then you will know later that we can take the inverse Laplace transform over its operator inside the parentheses. You can take it inside. So it is inverse Laplace transform of 1 plus the inverse Laplace transform of 1 over s. Okay, and we know the inverse Laplace transform of 1, which is delta, right? And the inverse Laplace transform of s is u. So that's it. That is our xt. Now, this is very easy. It may look very easy, but trust me, you'll see this on coming up later on, and everything that would come up will fall into this process. So the process is this: given xs, try to write it in the form that we already know, and then look at each term and find the inverse Laplace transform of each term. And that's it. That's a general idea. Okay, it should be easy. Now let's look at another function. This time it's exponential. It's the exponential signal. Exponential signal is xt equal to e to the negative at ut. One-sided exponential. Now, let's look closely at the exponential signal written here. So what we have here, we will be only interested in the case when a is positive. Okay, when a is negative, it is unbounded, and that would not be interesting. So we'll be interested only in the case when a is negative and x is bounded. And when that happens, the graph of x would look like this. So this is a graph of the decay exponential. Now, let's take a Laplace transform out of this one. So the Laplace transform of the exponential, right? E to the negative at ut. By definition, it is integration starting from 0 negative to infinity. And then plug in e to the negative at ut, and then e to the negative st dt. Now let's move faster, okay? Let's move faster. Now, because of the nature of u, right? Then we have to start from 0, right? To infinity, and then we can drop the u notation because u is 1 over in this interval. So we have e to the negative a plus s, and then t, and then dt. All right, and then we do the integration, which we know that it would be 1 over a plus s. Okay, that and the integrand and the parenthesis is e to the negative a plus s infinity minus 1. Actually, sorry. Let's take a look here. I think I for this one I did it the other way around, right? The first time around was correct. Sorry. So let's put negative sign there. Let's drop the negative sign there. Sorry about that. The first time around was correct. The second time around was not correct. Okay, now, again, this is e to the 0, right? This is e to the 0. E to the 0. And now this is 1, okay? This is 1. And this is 0 when the real part of a plus s is positive, okay? And when that happens, you're going to have 1 over s plus a when the real part of s is greater than minus A. So we have a conclusion that the decay exponential, which is e to the negative at ut, has the Laplace transform pair of 1 over s plus a. Okay. Now, if you notice here, if I set a equal to 0, if we set a equal to 0, then the exponential will become u, right? Because if we set a equal to 0, this will vanish. This will be gone into 1. Then we're going to have a u, and then we're going to have 1 over s, which matches exactly the previous signal that we did before. Yeah. This is the case of the exponential when a is set to 0. Okay, so they are consistent with each other. And also, the inverse Laplace transform of 1 over s plus a is e to the negative at ut. Okay. So, you with me, everybody? Not sure. Next week we'll have as many people as we have today. But let's hope. Now let's do another example. Now let given xs equal to I'm thinking, sorry. Let's do this one. Given this, we want to find xt. Can you do that? Can we do that? Remember the process, right? Remember the trick. We are not familiar with this one, right? This is something we have seen before. We haven't seen this before. But the trick is try to write this down into something that we have seen before. So what have we seen before? We have seen 1. We have seen 1 over s. We have seen 1 over s plus a, right? So try to rearrange this into something that we've seen before. Now, how do we do that? We know that we can write 2 over s squared plus 2s as 2 over s plus 2, right? Now, can you do this? Can you find this? Can you find these two numbers such that these two are equal? Can you do that? Of course you can, right? What are they? What is this guy? What is this bad number? Is it 1? Should it be 1? Should be 1, right? And this should be negative 1, right? So I know that I can plug this in as 1 and negative 1, right? And they are equal. Are they? Yeah, they are. So xt, right? Xt. Now, this we've seen before. And this we also seen before, right? So we are in a position to find the inverse Laplace transform. So the inverse Laplace transform 1 over s minus 1 over s plus 2. Now it is equal to inverse Laplace of 1 over s minus inverse Laplace of 1 over s plus 2. But the inverse Laplace of 1 over s is ut, right? And as for this guy, now a is 2, right? A is 2. See, look at that. Look there. A is 2, right? So it should be e to the negative 2t ut, right? And then 1 minus e to the negative 2t times ut. And this is the answer. Can you see the pattern? The pattern is exactly the same as in the previous example. Okay? Given something xs, try to write it into the form that, into something that we've seen before, then work on those, right? To find the inverse Laplace and then add it then back, and then we get the solution. Okay. All right. Any question, please? Oh, sorry. Here. How could I forget my first? It's too big. This is too small. Yeah. All right. Now, let's look at the properties of Laplace transforms. Some of the important properties. The first property is called linearity, which is the one. I think it is the most important property. By the way, I'm not going to prove every property. Okay, I'm not going to prove all of them because we don't have enough time to do that. Linearity says that if you take a Laplace transform of a linear combination between two signals. Okay, this is called linear combination. This is called a linear combination. Or it is a weighted sum. Okay, sometimes we call it a weighted sum. Sometimes we call it a linear combination. Now the result would be the linear combination of the Laplace transform themselves. Actually, I should. Okay. Right. So in other words, it's like we can put L here, L operator inside of the parentheses. Okay, we can distribute L inside of the parentheses to get this. So this is called the linearity property. It is one of the most it is one of the most important properties of Laplace transforms, and they're very, very useful here. Now, we have to note a couple of things. Okay, first, A and B can be complex numbers. Okay, A and B can be complex numbers. And second is that this is also true if we replace L with inverse L. Okay, also true with inverse Laplace transform. So what do I mean here? What I mean is, if you take the inverse Laplace transform of AXS plus BYS, okay, what you're gonna get is you're gonna get AXT plus BYT. Linearity goes both ways, both Laplace and inverse Laplace transforms. Now, let's look at some example to make you familiar with this property. We let the signal x equal to cosine of omega 0 t ut. Now let's find the Laplace transform of the sinusoidal here. We want to find xs. Now, to do this, remember what I've told you before. In this course, about 99%, whenever you see cosine or sine, you should convert it into complex exponential using Euler's identity, right? So we know that we can write from cosine of theta equal to e to the j theta plus e to the negative j theta over 2, right? We have this is from Euler's identity. We have xt. Now, the theta here, okay, the theta here is just omega 0 t. Okay, so whenever you see theta, you replace it with omega 0 t, and that would be fine. So we have 1/2 of e to the j omega 0 t ut, right? Plus 1/2 e to the negative j omega 0 t ut, right? And then we have xs, right? Which is the Laplace transform of the whole thing here. So I'm going to make a copy and then I'm going to paste it here to save some time. Okay. Right? I have that. And then I can use the linearity property. Okay, I can just simply put a small letter L here to indicate that I'm using the linearity property there. Okay, and make put the L inside of the parentheses, so we have 1/2 of the Laplace transform e to the j omega 0 t ut, right? Plus, I'm going faster now. 1/2 of the Laplace transform e to the negative j omega 0 t ut. Now, what do we know about the Laplace transform of exponential? Here, right? We can use this. We can use this formula, right? Now, A here, the A here is j omega 0, is negative j omega 0. So the first term is 1/2 of 1 over s minus j omega 0. And the second term is 1 over s plus j omega 0. Right? And then you can do the algebra to get s over s squared plus omega 0 squared. Now, going from here, okay, going from this line to the last line requires some algebraic manipulation. I hope everybody could do that, so I'm going to leave it to you, right? So we have a conclusion from this example that the cosine of frequency omega 0 t ut has the Laplace transform pair of s over s squared plus the frequency squared. Now, similarly, that was for cosine, right? And I would encourage you to do the sine as well. And you can prove that for sine, okay, sine omega 0 t ut. The Laplace transform would be omega 0 over s squared plus omega 0 squared. Now, how to do the sine? You could use this, right? To do the sine, you have to do e to the j theta minus e to the negative j theta over j2. That would be the sine. Okay, and that should be easy, not difficult at all. Okay, now the next one, sorry, that was the first one. That was the linearity. The second one is called time shift. The time shift property states that if you do the Laplace transform of x shifted by t0, everything shifted by time t0, okay, what you get is you're going to get e to the negative st0 and xs. This is a time shift property. In other words, in time domain, we have a time shift. Time shift in time domain means multiplying by e to the negative st in the frequency in the s domain. Okay, so whenever you do a time shift in time domain, in the frequency in the s domain, you multiply it by this exponential. That's a time shift. All right. So let's do some example. So we let xt equal to 5 e to the negative 2t ut minus 2. Okay, we want to find and y equal to 5 e to the negative 2 t minus 2 ut. We want to find xs as well as ys. Are they the same? You have to ask yourself first. Are they the same? X and y. Are they the same? They're not the same. Okay, they're not the same. So what is the difference between these two guys? So if you draw a graph that depicts x and y. Okay, let's do x first. To do x, right? To do x, what you do is you draw the decayed exponential there. Okay, this is supposed to be 5 e to the negative 2t. Okay, this thin line is supposed to be 5 e to the negative 2t. Now, x, the ut minus 2 means that the graph of x should start at time 2 on. Okay, and it should start at time 2. So we have to locate time 2. Right? We have to locate time 2, which is, let's say it's here. And then the graph of x should be this orange line. And then now this is x. Okay, can you see? This is x. Now what about y? For y, you have to draw this first. Okay? You have to draw this. So what is this? This thing. What is this thing? This thing is exponential 5e to the negative 2t shifted to the right by 2 time units, right? Look at y here. Let's forget. Let's ignore ut for a while. Let's ignore ut for a while. So this guy, this thing, this function, this expression is 5e to the negative 2t shifted to the right by 2, right? 2 here means shifted to the right. So to draw y, okay, you have to shift this orange, thin orange, to the right by 2 time units. So when we do that, we have well, let's copy it, right? We can shift it to the right 2 time units. It's exactly here. Here. See? Look at this line. Look at these 2 points. See, shifted 2 time units, right? Instead of this value, okay, this height, instead of happening at time 0, it happens at time 2. So shifted 2 time units. So the thin green line here is 5 e to the negative 2 t minus 2. I should extend it. But then we have to multiply by u, right? So that means that it should start at time 0, okay, to the right. So the function y would be the green one. And it would look like this. This is y. This is y. So are they the same now? Of course not, right? They're not the same. So that means that Laplace transform should not be the same as well. Now let's try to find the Laplace transforms of both of them. Okay, they're not the same. Now to find x, let's find x first. And it is the Laplace transform of 5 e to the negative 2t ut minus 2. Now, how do we do that then? We don't know this one, right? Because when we did the Laplace transform, everything was ut, right? Everything was ut. We're trying to use this one. We think of this formula, right? But hey, this starts at ut. It doesn't start at time t minus 2, right? But the problem that problem starts at time t minus 2. So we think of this. We think of time shift. Time shift means that if you plug t0 as 2, right, we should be fine. But we have to be careful because simply shifting u is not enough. We have to also shift the x as well. It means, you see, look at this. When we do time shift, we shift both of them. We shift both x and u. But here, this only shifts U. It doesn't shift X. It doesn't shift this guy. So what to do? We have to rearrange it so that this becomes T minus 2. Right? Inconsistent with T minus 2 here. So let's make some magic happens by writing it as, let's take 5 out of the Laplace operator, e to the negative 2 t minus 2, right? And then ut minus 2. Now, if I simply write this down, would it be correct? Of course not, right? They're not the same, right? Because this one has the factor of e to the 4th in excess, right? So I have to eliminate it by dividing it by e to the 4th. Here. Okay, to make them equal, right? And now we are in a good position to do the time shift. So this is 5 e to the negative 4. I think I should do this. 5 e to the negative 4. And then this is simply the time shift. Now we can do the time shift. E to the, now t0 is 2, right? E to the negative 2s. And Laplace transform of e to the negative 2t ut. Okay. But then we recognize that e to the negative 2t ut has a Laplace transform 1 over s plus 2, right? So 5 e to the negative 4 e to the negative 2s over s plus 2 is the answer. Okay? Now let's do y. Y is the Laplace transform of what? Of this. Now y is easy. Y is easy. You know why? You know why y is easy? That's because, see, for y, we can take the 2 out, right? We can take the factor 2 out of the exponent terms to get e to the 5e to the 4th and the Laplace transform of e to the negative 2t ut, right? Okay? And that's easy. This is not time shift at all. It is 5e to the 4th over s plus 2. Okay? So that's what we have expected. They should not be the same, right? They're not equal. I know it time's up. Let me give you one last example, and before we leave, unless you don't have any question. Now let's do another one example. Rectangular pulse. Suppose we want to find the Laplace transform of this signal. Can you do that? Can you do it? I want to find the Laplace transform of this one. You think you can do it? This pulse, we call it rectangular pulse because it takes the form of rectangle, right? So we call it a rectangular pulse. The height of this pulse is 1. The width of this pulse is capital T. Now, You have two ways to do it. Either use the definition of the Laplace transforms or use the properties that we have seen before. Now I'm going to use the properties that we've seen before. So I'm going to start with write x as ut minus ut minus capital T, right? So xs would be Laplace of ut, right? Minus Laplace of ut minus capital T, right? Now this is from the linearity property. Okay? And then I know the Laplace of u as 1 over s. What about the Laplace of ut minus capital T? That is a shifted version. That is a time shifted version of u, right? I know that in the time domain, we have the time shift version. In the s domain, we have to multiply by e to the negative st. So minus e to the negative s capital T here. And 1 over s. Okay? And in the end, we have 1 minus e to the negative s capital T over s as the answer. So this is the Laplace transform of the rectangular post with capital T and the height as 1, starting from time 0. Okay? All right. So that's it for now. Unless you have questions. Let's stop the recording.